4:10, and I think we have more than a quorum. So on behalf of the College of Engineering, on behalf of the Department of Electrical and Computer Engineering, I'm absolutely honored to welcome this afternoon's speaker. His name is Jerry Woodall, and I'll tell you about him in a second. But he is a professor of electrical and computer engineering, the Barry and Patricia Epstein Distinguished Professor at Purdue. If I went down the entire list of all his accomplishments, we'll be here for a while. So I'm going to be brief, and he wants to go to the reception. He is an electrical engineer and a pioneer in the research and development of compound semiconductor materials and devices. In fact, his research has enabled about half of the world's annual sales in compound semiconductor components. He invented the red LEDs used in indicators, stoplights, and electronics in CD players, TV remote controls and computer networks, high-speed transistors used in cell phones and satellites, and the weight-efficient solar cell. The technological and commercial importance of Dr. Woodall's seminal work led to the 2000 Nobel Prize in Physics for heterojunctions, awarded to Herb Kromer and Shores Alferov. He is a National Medal of Technology laureate. He's collected over 85 patents in more than 350 publications in the open literature. Many honors and recognitions, such as the Electrochemical Society, the Institute of Electrical and Electronic Engineers, and the American Vacuum Society, and the Federation of Materials Society. He was elected to the National Academy of Engineering in 1989, and an AVS Fellow in 94, an IEEE Fellow in 90, and an ECS Fellow in 92. He has a BA in Metallurgy in 1960 from MIT, and I have just enjoyed a great hour with him sharing in what I've just discovered are many people we know together and many stories that you made my afternoon, Jerry. It's been fun. So it really is an honor to welcome someone of Jerry's caliber to be with us today, speaking about high-impact alternative energy R&D at a university. Jerry, welcome to Davis.
Thank you.
Jerry, before I start, I did want to ask Rick Hill to offer a few words, since he is the chair of the host department.
One thing left out was where Jerry did some of this work, and a lot of it was done at IBM T.J. Watson Research Center, Yorktown Heights, New York. I happened to overlap with him there in the late 80s and early 90s, and I can say that without a doubt, Jerry was the most creative, charismatic, and outspoken character at IBM. And I think you'll see parts of all of that in his talk today.
Thank you. So, yes, that comment about IBM is actually important, because I used to think that being at a corporate research laboratory would train me properly for being a professor, and it sort of did, except there was one problem. So yes, I had to do something that was not on IBM's mainstream, and it was outside the box. I had to seduce people to do research, and as most of you know, if you want to do collaborative research, you've got to find a colleague and get them interested in it, and go get some money and all that sort of stuff. So the part that failed me, as I will show you in a minute or so, was IBM didn't train me to be nice to program managers. And so that's a bit of problem which I'm trying to fix. We'll see if it all works out. So yes, this is an arrogant title, High Impact Alternative Research, or Alternative Energy Research and Development at a University. It shouldn't even be there, but the things have changed so much that the ground rules for doing this kind of stuff are almost very impossible to meet nowadays. And I want to say a few words about that. And if there are any program managers in the crowd, you can step outside and go to the men's room while I rat on you. Okay, so you know, we teach our graduate students we ought to have an outline. So here's one. So why is it tough getting agency funding to do innovative research at a public university? The key here is public, because places like Stanford and even Yale and others, where they are not public, the ground rules are a little bit different. So I'm going to spend a few minutes talking about that. Then I'm going to summarize two of my research programs One is what I call off-the-roadmap photovoltaic programs. I've enjoyed talking to colleagues here about some of these issues. And then finally, something I got into a long time ago, water splitting with, I discovered that DOE likes the word earth abundant. How do you like the earth abundant? Translational, transformational. Earth abundant is a new keyword. Light metals to make hydrogen on demand, okay? All right. So, yeah, I'm proud of this. I want to show you something. This is a lead-in for something related to this. Okay, so President Bush, in 2002, gives me a National Medal of Technology. So, great. I want you to read it, though. Technologically and commercially important compound semiconductor heterojunction materials, processes, related devices such as light emitting diodes, lasers, and ultra-fast transistors. I'm not trying to be arrogant. Look at this word, solar cell. Now, are you ready for this? Watch this. Oops. Oh, so I want to set the stage. I actually did something. So I'm very proud of this thing. I had to write the Secretary of Energy to get this point put on the NREL graph. If you have an old graph, it's not on there. I couldn't get Larry Kazmersky to do it. And so I wrote Steve Chu a note, and so Larry got annoyed, so he put it on there finally. Notice, 1977, 22%. Silicon was about 12 or 13% then, and we held this record for a long time. So that was one of the reasons that thing was in red. Okay, here's the background. Now watch this. Read it. No track record, no medals, no nothing. These criteria permit an evaluation of the proposal's technical merit, give me a break, creativity, educational impact, benefits to society. Say what? All right, so here we go. It's time to rat. So I had given this lecture, part of it, or a similar one, to my colleagues down at Ohio State University. They were having a materials week down there. And the provost was asked to be there. So she was sitting in the audience watching all this stuff. So what happened to funding for high-impact seed R&D in America? The good old U.S. government agencies and U.S. companies, stockholders, killed it. And then it rose out of the ashes and was reborn in the Pacific Rim. Your ECE chairman knows all about that. He spent some time over there watching these guys take off like big birds on some of this stuff while we decided we were going to use metrics. Let's step back for a moment. So I always like to think about what are universities for? So this is a kind way to put socializing students. Some of that stuff is not the best activity on campus, especially if it involves an organic called ethanol. But anyway, so this is whoops, sorry about that. So this is a good way of putting it to prepare graduates, their students, for productive members of society, blah, blah, blah. But for me, what I do is I like to train my students to be entrepreneurs via research and thesis projects whose scholarly is key word with me. I don't just do rebuild engines, although that's fun, engineering topics, and could lead to commercially viable products. So a lot of my colleagues at Purdue kind of look at this statement with askance because they have been chasing the money for a long time. And so for some guy whose career at IBM was based on innovation and invention to show up with this kind of thing, especially at Yale, didn't sit well with everybody, but so what? Okay, so here's my research model. So when a student comes into my office, I say, let's look for a market-driven or new or improved device function, okay? So I've updated this. I was working on high-speed devices, now it's solar cells, that can realistically be made economically viable. It's key. I don't want to just make higher efficiency stuff. I want something that actually gets out there and gets used by some venture capitalists. So I sent him off to the parts bin. Go to Radio Shack and see if you can find what it is you want to work on. If it's there, go find another professor. But if not, come back and we'll talk turkey. So we'll integrate materials design. So I'm really a material science person masquerading as an electrical engineer. So far, I haven't been put in jail for it. I don't think I will be. But my background, as you already heard, is I was a metallurgy major. Metallurgy is the earlier word for material science. Okay? So we're going to integrate materials design into a functionality solution, develop what you'll see in a few minutes, an MIS-type compound semiconductor solar cell, and a cost-effective photovoltaic stack for concentrator systems. So I'm going to talk about this a little bit later. So that's my model. Sounds great, right? How did it work out? Well, at IBM it would have been great, but not at a university. So it was almost a total failure. Watch this. Between 1999 and 2010, I had 0 awards for 35 agency-submitted proposals. I had one with Carl Hess at Illinois. I had one with Gene Fitzgerald at MIT. I had all kinds of people I went with, and nothing came out of it. None of the eggs hatched. But I put this together when I was still at Yale. So I had 2 years of solar cell funding from a Yale Angel alum, and I had 1 year of detector funding from one of my co-founded startup companies. So I had some funding, but it wasn't totally bleak, but nothing from the agencies. What went wrong? You all know what went wrong. So suddenly we had governing boards to install metrics to improve efficiency and told directors and program managers what would be funding. All winning proposals had to respond exactly to what a BAA or RFP, etc. requested. This resulted in writing competitions, grantsmanship, and chasing the money rather than funding the best realistic idea proposals. Am I talking to the right crowd here? All right. Analogy. Imagine an artist competition where the contestants are given the same paint by numbers palette and the winner has the fewest smudges. That's basically what's going on with the agencies right now. If you don't believe me, just see what your rejection rate is. Okay. What went wrong? So the principles of market-driven, not bad actually, but market-driven and mitigating risk kill the self-idea-driven R&D both at large caps, say IBM, Intel, and startup companies. Also, most large cap companies don't want to fund universities to invent the next generation technology because of the Bayh-Dole Act doesn't protect LC company IP investments. Now, maybe most of you don't know this, but if IBM were to give you some money to develop, say, a 22 nanometer node integrated circuit, and it all worked out, California would own the patent because it was done in a federally funded environment. What the Bayh-Dole Act does is it allows the government to take a royalty-free license of that work and give it to a competitor. Now, if you're an IBM president, you ain't about going to do that. If you are a small startup, no problem. Bayh-Dole doesn't bother you. You just want to get out there and get some money going and get bought up by a big company. So this wonderful thing called Bayh-Dole actually is a big pain in the butt. Now, so you say to me, wait a minute, Woodall, I know guys who are working with Intel and other companies, they're giving me money, but they're not giving you money to invent next generation technology, and you don't get to go into the most holy place where they're making products. So if you do, you've signed a non-disclosure agreement, you probably won't get money for funding there. What you'll do is you'll get scholarships for students and everything else. So this was a seemingly a great thing to do, and it's time to get rid of it. I have a solution for this, but I'm not going to go, that's not part of what I'm going to do today, and I will talk about it separately. Here we go. You want funding? You have to do what they want, not what you think is important, even if your ideas are demonstrably better for U.S. science and or technology, hence U.S. prestige and the economy. Then grantsmanship kicks in. Furthermore, there is metrics, outreach, K through 12. Pretty soon it'll be post-WUML, postpartum, translational, transformational, multidisciplinary, blah, 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 blah. You know what I'm talking about. Now, there's nothing wrong with doing that. But if you want to do research at the graduate level, I ask you, what is K through 12 going to do for that? Just ask your department head and the dean how much time doing administrative work takes away from what they want to do in the research lab. They do it anyway because they're good guys. But this is a big problem, folks. Okay, so here's what we do if nothing happens. Not everybody will still do this because people are used to doing it at university. You try to write compelling proposals every night on useless agency topics. Cope with a 9% rejection rate. Feed your students till they graduate. Pay cost centers to use shared equipment. Go to conferences at nice places, maybe. Write progress reports every quarter. Attend program reviews. And listen to colleagues exaggerate their accomplishment. Boy, I hit a raw nerve there, right? Teach. Serve on committees. And those of you who are tenured, you go to primary meetings, after which you leave with the rest of the guys of the rest of the walking wounded because someone tried to pass a motion. You said, is this person brain damaged? And that's the way it goes. So you do this over and over for 50 years until you die or retire. Okay, but it's fun. Students are great. I'm going to give you two things to think about. One is sort of based on the second one I will go over is based on the old MIT method. The first one's a little bit different. So one thing to do is to fund teams led by senior or mid-career internationally recognized stars based on track record rather than just grantsmanship. You've got to write something that's worthwhile, but it doesn't have to be a grantsmanship contest. Okay, so you feed your students and finally you retire. Model number 2. Now this is sort of the MIT thing. And I think it's worth thinking about. So we have the agencies fund schools and departments in proportion to their international ranking. Okay, funds will be doled out using local criteria rather than panels composed of jealous competitors. Now think about it, folks. Wouldn't you, even though you have a colleague you can't get along with, wouldn't you rather have that person, you take them out to dinner, give them a beer, judging whether you should get some funding rather than some panel down in what's the name of Boston, down in Boston or someplace like that? Those guys are going to rake you over the coals, and you have no way to get back at them, unless you know where they live. Okay, so I think this is actually a worthwhile thing thinking about. It keeps department heads on their toes, deans on their toes, and so yeah, MIT will get a lot of funding, but so will you. Well, guys that won't get much funding are ranked, 230th or something like that. So I think this is actually a good system because once the funds come in, then you can compete locally rather than down in Boston on trying to get the money. And I would rather do that. I would certainly kiss and make up with colleagues I didn't get along with for doing that. That'll help us read a core. So those are the two things. Summary thought, and we'll go on to the technical part. If stock and stakeholders and agency continue with only a business as usual policy, the U.S. will become, I actually claim it already is, I need to update this, a third-rate country with respect to leadership in breakthrough and innovative science and technology that is followed by U.S. companies commercializing the innovation. Now, Davis happens to be near lots of VCs. I think that's a good idea because what you can do is that you can start interacting with companies. And so I say, I, for one, choose to engage industry rather than wait for the U.S. agencies to get their act together. Republicans and Democrats are killing each other every day, Jeez, it's really gotten amazing. It's like a war down there in Washington. So these program managers aren't going to do anything. for a while, but with a lot of VC money in the economy, look, you read the newspaper, all these companies are making zillions all of a sudden. So there's money out there. And to drive this home, I've already started 5 companies and 3 are still alive, which is not a bad deal. Finally, ain't it a shame? Successful entrepreneurs know where to go and can drive the car. Critics know where to go but can't drive the car. Agency program directors and managers don't know where to go and can't drive the car. Unfortunately, they own the car. Okay, it's time to be serious. Okay, so as Rick pointed out, we used to be colleagues at IBM, and those days heterojunctions were hot and a lot of new devices were exciting on the horizon. But what's happened is that the semiconductor business is really maturing there. There's still stuff to be done, but I've decided that I don't think our energy problems are going to disappear. We keep talking about them. So my program is all about energy and actually clean water. So I have 3 energy programs. I will explain each one of them. Gallium phosphide is the material of choice to make the top solar cell for a tandem stack. I will carefully explain that for concentrator systems that will achieve 50% conversion efficiency. So this guy could be next generation. The reason is this material has been around. It was a material of choice for red light emitting diodes at Bell Laboratories back in the late 60s and early 70s. More recently, we're going to be making gallium arsenide and gallium phosphide MIS solar cells. I'll tell you what that means in a minute for both thin film, low-cost applications and concentrator applications. This is just being started, so I call it upstream. And finally, I learned how to split water with a bulk aluminum-rich alloys to make hydrogen on demand. And actually, that's ready right now, which makes it a problem for me. I have to find somebody who wants to do it. So let's talk about solar cells first. Okay, so you'll forgive me. I want to bring everybody up to speed on solar cells. Now, you all may be experts, but I want to use this 2 diagrams to point out what needs to be done. This is actually a photodetector rather than a solar cell because it's reverse biased. In other words, it's negatively biased. So here's a lecture. Photons come in. Wiggle, wiggle, wiggle. Lots of them get absorbed here. And finally, way over here somewhere, there's a guy who hasn't been absorbed. And then there's all the photons that are lower than the band gap energy of the semiconductor. They just go on through. So here's the problem of a solar cell. And a lot of people don't realize, to keep track of this. When I generate a minority carrier, I make an electron hole pair on the p-type side. The idea of a solar cell is for these electrons to cross the junction and these holes on this side to cross the junction because I want to get current. You know, photodetectors don't work. There's not much of a market for them. What I want to explain to you is this region right here. This is a big deal because it turns out the way semiconductors work that high energy photons get absorbed right close to the surface. So I use this to represent carriers that don't have diffusion links long enough to make it across here, or they just recombine. Carriers that recombine either give heat or light, and that's not very useful for a photodetector. And furthermore, with surface states, there's something called reverse band bending, which drives carriers the wrong direction. Okay, so that's the lecture on collecting current. The light current is in this direction. Electrons are flowing this way. Holes are flowing this way. Everything in this little W is called the depletion width. And this little symbol here is the electron minority carrier diffusion length, a property of the material. To make L big enough, especially in silicon, the silicon has to be good quality. Good quality silicon ain't cheap. Okay? So in order to collect everything in silicon, I need to make the stuff pretty damn good. So we'll talk more about that. And so if I look at the equation, the generation of carriers, a function of lambda and distance, I have the stuff that comes into the surface times an exponential e to the minus alpha x, okay? And that's why this little schematic shows the thing doing that, okay? But solar cells aren't photodetectors. Solar cells is no good unless you get power out of it. So I suspect there are a lot of electrical engineers in the audience here. So this is the IV characteristic under light. It's flipped upside down because the current is negative. The voltage is power. They're out of phase. And those of you who take an electrical engineering course that talk about emission of power absorption, a negative current and a positive voltage means I'm emitting power. The best I can do to get power out of this is the maximum inscribed rectangle. So I want a diode that has a very sharp knee. There are points on here that are important. The short circuit current is a negative current, and open circuit voltage. That's what happens when you snip the wires and you let it become forward biased as a result of light coming in there. So end of lecture. Now you have enough to pass the exam, so here we go. Here we go. There's basically two ways to do it. Okay, so the guys in the fossil fuel business, folks, they ain't going to give up fast. They're making billions and billions, and they're not going to give you their business. So whatever you do, you're going to have to make it cost competitive. Low cost, low cost. Low efficiency, well, modest efficiency. So here we go. Back to the diagram here. Here are my blue photons. They get absorbed near the surface. Stuff goes all the way through. It's lower than the band gap energy. But check this out. When I bring in a blue photon, I have a band gap that's, say, red or infrared. This excess energy, I lose by thermalization of this electron back down to the conduction band, and that's a loss. And the stuff that goes through is a loss. And so people have worried about this theory, the detailed balance theory of Queisser and Shockley. So the best you can do with a single material with staring at the sun is about 30%. If you concentrate, it may 35%. So if I'm going to use one material like cadmium telluride or high-cost silicon, cadmium telluride, these are the kinds of commercial efficiencies. So this guy is, say, organics. This guy is solar power, Dick Swanson. He can make some really good stuff, but they're very expensive. So right now, to my knowledge, cadmium telluride is the material of choice for cost effectiveness. It's low efficiency, low cost. They claim in the press that they can now make cadmium telluride cells, large area, but not the system, for about a little less than $1 per watt, which is a pretty good number, but by the time you mount it and put it over a large area, it's going to cost a lot more money. The other key thing here is I don't care how low cost it is, you can give it away. If it's less than 10%, unless you want to have a niche application for a watch or something like that, 6% is not going to make it. As I said, there's plenty of niche market stuff that it might, but if you want to do this and cover the world, you're not going to do it with a 6% cell because it's just not cheap enough. The oil guys are not going to give up. Okay, so the other guys, the other way to do this is take a stack of materials. So here we go, large band gap. So I have stuff that just barely absorbs blue light, so I lose very little energy by this thermalization process. So the blue photons get absorbed. Then I have another band gap lower, connected in series, where I absorb the green photons, blah, 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 all the way out. Commercial efficiencies are anywhere between 28 and 39% concentrated. So the idea is these suckers are going to be really expensive, and we're going to put the cost in Fresnel lenses and stuff like that. Now the problem is, on a cloudy day, you can't track the sun, at least not where I live. Boy, we've had terrible weather in Indiana. It seems like every day there's clouds come in. Anyway, so this might be good here. This might be good in UC Davis. You know, a lot of sun today. So this is another way of doing it. The idea is that the system efficiency or the cell system of these stacked solar cells has to be really high to recover the cost of putting lenses and power conversion and inverters and stuff like that, okay? This is it. Okay. Now, I want to show you a figure that my student did for his prelim just last week. So let's take a look at multi-junction solar cells. I'm going to talk only about the top cell band gap. And the reason is, what I'm going to explain to you is that to get the best cell, there's no material out there that will do this right now. And we think gallium phosphide has got a good shot at it. So let me explain this. So I go all the way from one junction, which is a single material, say silicon or gallium arsenide. So this is the top cell, okay? So this is what you would find in Shockley-Queisser paper or Henry's paper. You know, you go to high photon energy, the efficiency drops off because even though the voltage goes up, I don't get much current. So it peaks, this is the sweet spot for a single junction. So you can see what happens if I go from 1 up to 6, that these are all top cell optimizations, okay? So if I get up to 4 junctions, so I got 2 figures here. One is for 1x and one's for 1,000 suns, okay? So here is say a 4-junction cell, okay? And we can plot that a different way over here. Let's look at just a top cell band gap, okay? So we go from 1.6 to 2.4. So here's 3. And so it's amazing right now. So this air mass 0 is what the spectral distribution is outside the Earth's atmosphere. So we only care about the red and the yellow. So this guy here, the red and the yellow, okay, are the band gaps of gallium indium phosphide. And these are put on top of gallium arsenide. And the guys have DARPA contracts are using lower band gap cells for the other cells. They're 3 and 4 junction cells. Notice that if I go to 4 to 5 junctions, I have to raise the band gap, and there ain't nothing out there that's working yet. Just doesn't exist, okay? Oh, I'm standing in your way, so you got to yell and scream when you can't see, okay? Okay, so here is a list of band gap menus. All right, here's good old zinc selenide, a non-solar cell, good UV detector material, zinc selenide. So you got to pay attention to direct band gap semiconductors, which don't have you don't have to have a very thick layer to absorb all the photons that can be absorbed, and indirect like silicon, where you need lots of material, cheap but lots. So here's germanium, here's gallium arsenide, aluminum arsenide, zinc. They're all lattice matched. Now, why is that a big deal? Because cells that have lots of defects don't work so good. Remember, the whole idea is to make really good cells for concentrator stacks. So one wants to find a decent substrate. So here's silicon and gallium phosphide. So it's conceivable that we could just make a single tandem cell of gallium phosphide on silicon and get up to 30%. We're looking at that carefully. So my student is actually trying to make alloys of zinc selenide, which is right up here, 2.6 eV, with gallium arsenide, make quaternary alloys, and it's been a very difficult path for him to do so far. So we will still continue working on that, but we need to modify how we're going to go about making the materials. I want you to check out gallium nitride, another material that doesn't absorb solar energy very much. Indium nitride, wowee. So if I connect all these together, I can make anything I want in the alloys. It's been tried over and over again. For those material scientists in the audience, something called phase separation occurs. And when you have phase separation in a solar cell, you're out of luck. You'll have a nice little paperweight that's pretty sitting on your desk. Now, my friendly colleagues at Berkeley, not too far away from here, still think they can do it. Good luck. I will hold my breath. This stuff here, silicon carbide, is indirect. Yeah, you say, well, gallium phosphide is indirect also, but the direct band gap, so I will show you in a minute, is very close to the indirect gap, unlike for silicon. So it has a shot of winning. So here's what we've done so far. So here's a schematic of how it would play out. So we have all these other low band gap cells, and we'll put gallium phosphide on top. Okay, gallium phosphide could add 17% to the 41 that's out there if it's perfectly optimized, but nothing ever is. You always have to derate efficiencies. Well, so far we've gotten the world's largest VOC for a real solar cell. Gallium nitride is not a real solar cell. It has a bigger VOC, but it doesn't detect solar photons. So far, indium gallium nitride does not work. And gallium indium arsenide phosphide, which has a VOC of 1.5. So we're fairly proud of this, but let me show you the problem. Okay, so for those of you who speak absorption coefficients, let me tell you what this curve is. Here's the absorption coefficient, reciprocal centimeters. The bigger the number, the smaller amount of material you need, which is a good thing. Okay, so here's the band gap, indirect gap of gallium phosphide, 2.26. The direct band gap occurs only a half an EV above it. So that means that for the blue and green photons, if I collect them efficiently, I can possibly get to these kind of numbers. So we think that we can get to a VOC of 1.85, these kind of currents, and that would lead to a component efficiency of 12.4. You add that to the 41 and you're up to 50. So we think this is a way we'll get there, but not what we've been doing, and I will show you why. So I had a student work on this. He's now at Arizona State. Okay, the problem is I want you to look at this little thing over here. The current internal quantum efficiency is a function of wavelength. Okay, so this peak in efficiency occurs at a wavelength where most of the absorption is occurring where there's a high electric field near the p-n junction. This drop off here is due to the fact that the minority carrier diffusion links aren't all that good. This problem, which is the worst, is due to a surface recombination. So as a result of all this effort, we were able to get to about 2.5% efficiency. Nothing to write home about, but he did a good job on his thesis, so he got his PhD and was able to get a job. Charles Allen. So doesn't look good. So we got to worry about that, and I'm going to show you what we'll do about it. Okay, so meantime, I went back to something I had done with gallium arsenide using liquid phase epitaxy. And so here is a liquid phase epitaxy melt. So here is a melt with gallium in it, maybe some phosphorus. But for the case of gallium arsenide, we would stick the substrate in here, and this melt would getter out impurities from the substrate. Now, substrates are really lousy solar cell materials because they have all kinds of impurities and traps and defects in them. But this solution will getter out stuff that kills the minority carrier diffusion links, at least in the region where the solar cell is made. So this was a key ingredient when we made our record gallium aluminum arsenide solar cell. So we tried this for gallium phosphide. Now, the way you read this is you look at normal photoluminescent intensity at 4 degrees Kelvin. Remember, this is an indirect band gap material. We use an exciting wavelength of 325 nanometers. So the wafer, as received, has this spectrum. Okay, so here's the band edge stuff here. So this is zinc sulfur pair recombination. Here's the exciton, free exciton line. P2 is oxygen, zinc oxygen pairs nearest neighbor, which kills lifetime, and there's some distant neighbors, P3. So we stick this thing in a melt at 900 degrees C for 30 minutes, and we get the blue curve. So this thing has been nuked almost, and so the question was, did this really do anything good? And the answer is, you betcha. So we made spectral response, amps per watt, out of small solar cells. So here is the as received stuff, arbitrary units more or less. And here it is as a function of wavelength for the getter. So now we have a way of taking crappy substrates and making it work. Now the rest is to make a decent cell out of it. Oh, by the way, so the one of the reviewers of the paper that's being published in whoops. Yeah, it's just appeared in Journal of Electronic Materials. He writes back and say, well, this is very nice. How do you know you didn't getter out the doping? So we did the CVs, and we couldn't see difference in the carrier profiles and stuff like that. So he was happy about that. So this has been just recently published. We're very excited about this, actually. Okay. Metal semiconductor photovoltaics. Why are they good? The reason is all I need is either N-type or P-type material. I don't have to make a P-N junction. That's the good news. The bad news is I have to put a Schottky barrier on there. And this barrier height's low. My VOC is going to be very limited because the so-called dark current, J0 here, will be very high, and VOC will be very low. So I get lots of current, very bad voltage, not so good. Okay, so the other problem is I got to get the light through this metal Schottky. So I have to make it thin, and I might have sheet resistance problems and all that. But the nice thing about this structure, and I want to point this out, is right near the surface, I have a nice big drift field which will take all these UV photons that are absorbed and drive them into the metal. The holes will go into the metal in this case. So there's no dead layer, so the UV response will be fantastic. So that's the good news. Simplified fabrication, no lifetime reducing high temperature process. Well, you can make this depletion layer fairly wide depending on the current, the doping level. No surface RG. And we can use this for polycrystalline thin films. Well, not so great, but Martin Green over in Australia reinvented this thing with silicon, where he used silicon MOS technology, took an N-type silicon substrate, put a very thin oxide so that the minority carrier would tunnel through, put charge in there which would cause the band bending so that the Fermi level is right near the valence band. So basically what you've done is you've induced a P-N junction with charge in the oxide. So this is being made commercially, actually, over in Australia at least. And so this is a really cool idea. So we said to ourselves, okay, but it hasn't been done anything else. So we're going to do this type 1 MOS device with compound semiconductors, and then we're going to look at some stuff that was looked at Stanford back in the 80s and use a metal heterojunction where we have an enhanced Schottky barrier solar cell. So we're going to do two things with that. Okay, so again, this is just more about the MIS type. So the point is that the point is the dark current, which determines in the denominator, it's a small number, you're going to raise VOC. Basically, you have a induced P-N junction device, so there's no dead layer. It's going to be a really good UV device. Now, the problem I say is it's made out of silicon. I need lots of material, and I'm going to need good quality material to collect the carriers that are generated by photons that are absorbed just above the band edge, which will go in deep into the sample, okay? So type 2, and this is from a figure from Jim Harris's paper, is we make a heterojunction where we have a larger band gap offset. So we have carriers that will either go through this notch, or we design it, we're going to use gallium indium phosphide to get rid of the notch, where we can move holes all the way to the metal that won't be blocked by any band offset. So we're going to make this actually a P-type substrate with this on it. Again, I don't have to do a P-N junction on this. If I get the barrier height, effective barrier height high enough, you can make J is 0, small, and then you can make a large, get high current voltage efficiencies. Okay, so those are the two things that my student's working on, just to summarize it. So we're going to do the gallium arsenide-based type 1 because it hasn't been done before. And if it works, it'll be very interesting because we won't need to put a window layer on a solar cell, which I invented a long time ago. We can just get rid of the window layer and have a transparent thin oxide that will have. So it might be a cost competitive way, especially if we do this in indium phosphide. I didn't put this up there, but indium phosphide is probably even better than gallium arsenide because the Fermi level that gets pinned by nature is pinned near the conduction band. So if you have a p-type piece of indium phosphide, you automatically have an induced p-n junction before you even start. So now that we know how to get or out impurities, we're going to try the same. We're going to try to make an MOS-type gallium phosphide cell for the top cell. So since I'm running out of time, I want to keep moving. We can take questions later on. Okay, so let me finish up with a water splitting thing. So those of you who've dabbled in thinking about hydrogen, so there's lots of hydrogen, you know. I calculated that if you take all the water in the ocean and ask how much, what's the energy density in terms of the hydrogen you could get out of it, it's about 4 times 10 to the 25 BTUs. It's a big number. Especially since the whole world is only using 4 times 10 to the 17th BTU, so we got a long way to go. So there's no elemental hydrogen. It turns out that the hydrogen that we had escaped the planet many years ago. Just a light gas. Has enough kinetic energy to escape gravity, so it's gone. So we don't have it sitting around. So people say, okay. So the real problem with hydrogen, small volumetric energy density, high pressure gas, low temperature, expensive and dangerous. Hydrogen transport is dangerous. So people who've tried to play with applications using hydrogen sort of have a conundrum because they figure, well, if I find something that's worthwhile, I still have to face these issues. So my approach has been to use a safe, cheap, earth-abundant high-energy density material for storage and transport, port that can react with water and make hydrogen on demand. Turns out aluminum is great. It's the 3rd most abundant element on the planet's surface. So if aluminum could split water, the chemistry would be 2 aluminums plus 6 waters goes to 3 hydrogen plus aluminum oxide with 3 waters hanging off of it of hydration. Well, obviously I was able to do it, otherwise I wouldn't be telling you about it. Check this out. This is the volumetric energy density in this axis, megajoules per liter, and this is megajoules per kilogram. Okay, so hydrogen wins on mass density, really sucks on volume density. You can't beat aluminum. Silicon's pretty close. We're actually going to be doing a silicon. What I want to drive home is aluminum has the highest volumetric energy density of anything on the chart. Anything down here, ethanol, gasoline, gasohol, all this stuff. Lithium-ion batteries, folks. Your government is spending money like crazy trying to move this point somewhere. I suspect it's going to go down over here in the 3rd quarter. You didn't hear that from me. Okay, so good stuff. Check this out. 1 kilogram of hydrogen, 140 megajoules, 39.4 kilowatt hours. That's the high heat value, combustible energy. Kilogram of aluminum makes 111 grams of hydrogen, 4.4 kilowatts. For comparison, I can take a gallon of aluminum, 10 kilograms, I can get 44 kilowatt hours of hydrogen, diesel's 37, and a gallon of liquid hydrogen, because it's a density of 0.5, is only 10 kilowatt hours. Now you can go over to Munich, as you know, you can rent a BMW running on liquid hydrogen. And there's an 8-liter tank Dewar in the car, and an 18-gallon tank of gasoline with no luggage space. You can't park it inside the garage. You have to leave it outdoors. If you leave it too long, the hydrogen has evaporated away. Okay, so this is either good news or bad news. So the rest of the heat from this high energy density material comes out as heat from splitting water. The total energy is 8.8 kilowatt hours per kilogram. Kilogram of coal, anthracite, is 6.7. So people are always saying, so I make it a point with my students that we are not going to violate the laws of thermodynamics in my lab. So it takes, to do a round trip to get this stuff out, I got to put 12.9 back in. Now your buddy Paul Solomon saw this. He came to me, he says, well wait, you got to put energy in there to make this stuff. I said, well look, it took millions of billions of years to get gasoline. Yeah, sure, you already got the energy stored in gasoline. So he was giving me a hard time that I got to take this aluminum hydroxide back to aluminum. But once you buy aluminum, it doesn't go up the stacks. It's yours. You own it. That beer can is yours. Okay? So, from a hydrogen point of view, it's only 34%, so it doesn't look great because you can do electrolysis for commercial electrolysis for about the same efficiency. So, why am I excited about this? Because if I already have electricity in my car or my vehicle, I sure as hell don't want to downrate it and make hydrogen. So the whole point is I'm going to make my aluminum off-site and use the aluminum as chemical energy in whatever I'm going to use it in. That's the whole point of the talk, folks. So 68% ain't bad for the total energy. Okay, so I always ask the question, sustainability, large scale. So these are vetted numbers. The aluminum reserve in the plants across about 10 to the 13th kilograms, that's aluminum. That'll make 1.2 times 10 to the 12 kilograms of hydrogen. And this will give you 5 times 10 to the 13th kilowatt hours of energy. That's a lot of energy, folks. Remember, it's kilowatt hours. All right? Current worldwide production is 32 billion kilograms. But more interesting, if you go to all the recycling bins in the world, there's 400 billion kilograms of impure aluminum. Now, impure aluminum is not a sin in our case. It's good stuff because we don't need high purity aluminum to make this. So this is enough to supply 12% of the annual energy consumption. About 100 quad BTUs is what the number is right now in the United States. Total, not just electricity. So the point is, we have got this humongous inventory which can be recycled, unlike coal or gasoline. So that's why I say you should pay attention, okay? Now, some of you are going to write me an email and say, well, wait a minute, when I do electrolysis of aluminum, I'm using carbon electrodes. That's only because the companies don't have to worry about the carbon caps and stuff like that. It turns out that De Nora, a company in Italy, uses titanium borides, and there is no carbon footprint when it's done that way. So why isn't everybody else using it? Because De Nora owns a patent that hasn't run out yet, and they are charging an arm and a leg to license it to Alcoa and other organizations, and I checked all this out. Okay, I was supposed to quit at 5, right? Do I have any more time? I got to get your approval, though. Okay, so I've only got 5 more minutes, so don't worry. Okay, so I'm doing liquid phase epitaxy at IBM. You dissolve aluminum into liquid gallium. You add water. That's not exactly how I did it, but this is a good. After you do the experiment where you're bungling along, you give a talk, you don't want to tell people you're bungling along. So what you want to say is, yeah, I did it this way. So what happened? So here we go. We got a gallium in the tank. We got aluminum in solution, not a compound. So it diffuses here. It sees the water, splits it into hydrogen gas plus aluminum hydroxide. Nice, but only 1 to 2% weight percent solubility of aluminum and gallium at room temperature. Gallium costs $500 a kilogram. So we submitted a patent at IBM. I decided I didn't have the chutzpah to send this off to a journal because they would reject it, saying, what good is it? Because it's only fun. But I believe having fun's a good idea. So here's a phase diagram. See, yeah, I know somebody sitting in the audience who knows this phase diagram. Okay, see. So here's the phase diagram. The only reason what I want to point out to you is we started over here at IBM. We tried to continuously dissolve aluminum into this gallium, and it didn't work in the presence of water. So my students started making alloys. And so the way you look at this, all you care about is how much gallium is in there. So we got over the point where we're making 95% weight percent aluminum and 5% gallium. And then we discovered if we put indium and tin with it, we lowered the melting point from here down to 10 degrees C with the gallium, indium, and tin eutectic point. So look at this. Gallium is up to 20 weight percent soluble in aluminum. So it's a very unique phase diagram. There's no other phase diagram with light metals that looks quite like this, which is a challenge for me to do this because we want to do it in silicon at some point in time. So here's where we are. We can make solid, and they're solid-like bulk aluminum-rich alloys up to 95% weight percent aluminum, 5 weight percent gallium, indium, and tin. We call it our 95-5 alloy. It will split dirty water at temperatures between ice and steam. As long as it's water, it doesn't react with steam very well, but if you put it in a pressure vessel, you can take it, up to 6 or 7 bars, 150 degrees C, and it works just fine there. We have now a new 9010 aluminum alloy that has the gallium, indium, and tin that splits seawater. That gets me very excited about doing desalination, ocean vessels, and stuff like that. And more recently, we now can just buy aluminum with 5% tin from a vendor. It will not react with water. So now we stick that in a reactor with the indium and gallium, and so I will show you in a minute how it will work, and it works just fine. So now we have a stable aluminum tin alloy we can buy from a vendor, and then we can make it reactive by putting it in a mixture with indium and gallium, and it splits water. So here, let me show you that. Okay, so here's the process. Notice that we use a lot of water because at room temperature, the equilibrium reaction product of aluminum splitting water is something called barite. This guy here, aluminum trihydroxide. But if you heat it up to 70 degrees C, it goes from, may not get it back to aluminum oxide, but I can get it to boehmite, which only has 1 water hanging on it. So the point I want to make with all these lines is that, yes, I use lots of water, but we get it all back. So if we use the hydrogen dynamically, we get some of that water back. If we heat the aluminum trihydroxide up, we get the water back. And if we do the stuff in a Hall electrolysis process, we get the aluminum back. So bottom line, you can get all the water back, or at least 98% of it back. So that's really important to me. Here's a picture, artsy picture of an alloy splitting water. It's just a small chunk of it. So if we use that scrap aluminum, I was able to get a cost estimate of the scrap, this 400 billion kilograms of scrap. It's going to be somewhere between 45 cents and 60 cents a kilogram. We can make hydrogen for about 10 cents a kilowatt hour. Hey, what happened to this number? Geez, I didn't see 3 anywhere. So it's 4 now. Lithium-ion batteries, according to Alex Mueller, Richard Mueller's book, is amortized at $4 a kilowatt hour. Good luck, lithium-ion batteries. If you own a Tesla, no problem, it's pocket change. Now I want to show you what my student did to show how this works, and I'm done. Okay, so when you make the alloys up, you have these aluminum grains. There's some gallium in it because the aluminum will dissolve the gallium. So you melt the aluminum down, you cool it down. So all this stuff here are rivers surrounding the aluminum grains. So the aluminum dissolves some of the gallium. the stuff, this is all liquid because it won't work if it's solid. We've tested that carefully. So right here, this is like the IBM experiment. We split the water, we make hydrogen, the hydroxide, and the gallium and tin is mixed in with this because I'm using this up. And after it's all over, all the aluminum has been used and it's converted. We have a 95% yield with this all the time, no problem. So this is how it works. It's not a question of a different kind of oxide. It's a question of having grains of a solid aluminum with some gallium in it. We don't know exactly how much. We're still studying that. But we've studied this with, with EDAX and stuff, so we know this model is correct. Okay, so these are what you can do with it. Lots of fun things. I won't go into the details of that. Okay, so one of the painful things that I've learned living in Indiana where there aren't any VCs around is I get lots of emails, get a lot of people. So I get two kinds of emails. One comes from, God bless you, screw the oil companies. So I get lots of those. Keep up your work. And then I get some tire kickers who want to know more about it. And when they find I don't have a big system out there working for a demo, they say, well, that's very nice, Professor. Well, I'll keep in touch. That's like giving you the bird, so to speak. Okay, so anyway, so what I've learned is I've decided what I'm going to do is to use both the heat and the hydrogen. So I made this cartoon up for a PR that Purdue just released a few days ago. So we'll start here. So I can use solar farms or wind turbines to do the smelting. I need electricity and heat. So I put it on a train. I take it to the factory to make the alloy. Then I put it on a helicopter. Okay, so I drop this puppy into a remote location. Could be military. So so I drop in the alloy reactor, first drop only because once they have it, it's theirs. The fuel cell is going to be amortized. So this is off-grid drop-off, and so this doesn't show up very well. This is polluted water. So I can either take ocean water or this stuff, put it in the reactor. I get H2O, hydrogen plus spent alloy, which is aluminum hydroxide, plus the gallium and tin. I get potable steam. Heat or air conditioning, because I can use absorption air conditioning from the heat. Okay, so here's the fuel cell. So I can make electricity, and I get more potable water. Then I can store this stuff. Either I put it in a landfill, maybe, or we pick it up later, and around we go. There are no showstoppers in this. And so what I did is very carefully did a cost analysis of this. And basically you can make water for $1 a gallon and electricity by amortizing the fuel cell for 34 cents a kilowatt hour. Now, this may sound high. It doesn't cost you $1 a gallon when you go over to, I don't know what your favorite supermarket is. It's cheaper. But remember, there are no roads and there's no electric wires going into these military installations or these remote villages. So $1 a gallon is something the government would certainly be willing to pay. And this is a reasonable number to have some electricity, so you can call your friends over in Kenya and watch some TV, run your iPhone, blah, blah, blah. So that's it, and that's all I want to talk about. So I'm going to quit there because I've run over time. I apologize. I was going to tell you a little bit about the silicon, but we'll leave that out. We're just going to end with this slide. So thank you very much for listening.
So we have time for one or two questions. Thank you, Jerry. That was fascinating, thought-provoking, and a little bit scary. Please. Saif.
Want to turn the lights on? Somebody?
Yeah, I'll do it.
I got to see who's trying to track me down here. All right.
So in your Schottky barrier solar cell concept, are there multi-junction possibility?
Oh, absolutely. I'm just showing what we're working on right now. The students' goal for the first is to actually build an MIS structure. We have Peter Yee, who's had some success in making MOS gallium arsenide. So we're going to use his atomic layer deposition ALD system to try that on, and we'll see how it goes. But then you're right. We can actually think about, you know, tandem cells, and the reason is I don't need a tunnel diode to connect these things anymore. Thank you for the question.
Anyone else?
You mentioned silicon a few times, so what are the challenges in doing that one?
Well, silicon is, you know, you need 100 microns to get a good cell. So if you want to trade off to make a thin film, and you think you can live with 10 or 11% efficiencies in the thin film version, it might go. I mean, but the problem is you got all the electronics and stuff. You got inverters and stuff. They only last 4 or 5 years. So you got all these other issues that means that even if you can make the cell for $1 a watt, you're still going to have a systems cost that the coal guys are going to smile, thank you for contacting me, and that's it. I tell you, I've been there, done that. So if you're going to play the alternative energy game, you can either do something wild that they haven't done the physics on yet, which is fun. Having fun is the most important thing in life, by the way, so I don't knock doing that. But if you want to do it for real, you got to look at what is it going to be doing at the end of the day and how much it costs, and is it uniquely suitable for that application. You know about that stuff, so that's basically it. So I don't think silicon is the path that we're on. There may be some other schemes that people are working on that might pay off, but remember, you know, $1 a watt, that's cheap. I mean, look, you can buy a Honda genset for $400 for 5 kilowatts. Vroom.
Can we call this the cycle of Jerry? Well, Jerry, on behalf of the college and the Department of Electrical and Computer Engineering, I want to thank you.
Has it got some aluminum on it?
It's got glass. How's that?
Okay.
I want to thank you for this
Thank you.
great lecture. That was great. That was great. There's a reception following the lecture next door in the Kemper Hall. Please join us and you can converse a little more with Jerry.